takes constant time. That's not the case here because we're going to start with the polynomial f and we're going to take larger and larger powers, and it takes longer and longer as the degree goes up, but the algorithm is still basically the same. So I'm going to call it repeated squaring. So let me just show you an example. Let's take p equals 83. Okay, so I need to compute f to the 41. Well, what's f to the 41? Well, 41 is odd, so this is f times f to the 40, and f to the 40 is f to the 20 squared. Okay, so now we need to compute f to the 20. Well, 20 is even. Okay, so you get the idea. Okay, f to the 10 is f to the 5 squared. 5 is odd, so that's f times f squared, and then I guess f squared is f squared. Right, so then I run this backwards. I start with f, I multiply it by itself, so it gets a bit bigger. Then I square that again, that doubles the size. Then I multiply by f, which doesn't change the size very much, just a little bit. So now I'm at f to the 10, so then I double it again. Now I need someone else on stage, f to the 20. Now, what's happening is, as we proceed, the size is roughly doubling at each point. So the cost is going to be determined pretty much by the cost of the top level multiplication. Okay, and then then you can add things up like a geometric series. Okay, so the real question is, what is the cost of polynomial multiplication at the top level? That's really what's controlling this. So let's take a look at that. And again, I'm not claiming this is necessarily the best way to compute this large power. I think it's pretty close as far as I know. But you can probably save a constant factor somewhere, somehow. Ooh. Okay, so now we get to the fun stuff, right? Let's write m sub pn to be the cost of multiplying polynomials in fpx of degree, say, less than or equal to n. So two polynomials of degree less than or equal to n. Now, let me just emphasize that I'm working here in a bit complexity model. Okay, another common model for this sort of question is an algebraic model, where you count the number of operations in fp. And that's a reasonable model to use, and you get similar answers. But I'm really interested in the bit complexity, which means I have to take into account the size of elements of fp. Okay? It's harder work to multiply in f101 than it is in f2. Okay? Okay, so before I talk about this, I need to talk briefly about integer multiplication. So m int n is the cost of multiplying integers of at most n bits. Okay, now Bjorn mentioned before, I've worked a lot on this problem, and a few years ago I proved with Joris van der Herven that you can get n log n. And this is an annoyingly complicated algorithm which uses a lot of FFTs and other fun things. And as I said, I could talk for hours quite happily about this, but I'm not going to. Okay, so we have this algorithm. Now, what about this guy? What do we know about this? And here's where things get very annoying. So I'll tell you first of all what we expect to be true, which we cannot quite prove yet. We expect that MPN is O of B log B where b is the bit size of the polynomials. So if you take two polynomials over fp of degree n, and you look at the total number of bits to represent those polynomials, which is n log p, then you should get, you should be able to multiply them in time b log b. That's what we think is true. Now you might ask, why do we think that? Is it just by analogy? It's actually a bit more than that. I mean, analogy, sure, that's really a good reason. But the better reason is that we actually have proved this, but assuming some number theoretic hypotheses. Okay, so Joris and I have another paper where we prove that this is true, assuming something about small primes in arithmetic progressions. If you're familiar with Linux theorem gives you a bound for an upper bound for the least prime in an arithmetic progression. We basically need a really strong version of Linux theorem. We need a Linux exponent which is unreasonably, like, much smaller than anyone has any hope of proving. Now that's just a conjecture that holds, but it's actually much weaker than the standard conjectures about primes in arithmetic progression. So we have this situation where you know, we're here, and what we can prove is over here, and what we think is true is over here, and we need something in the middle, quite a long way from both ends. So, you know, surely it's true. Surely it's true. But this is a double lightning bolt problem. I've thought a lot about this, and I have zero idea what to do next. No idea at all. Anyway, that's a good problem. So let me show you one thing we can prove using the integer multiplication result. Okay. So here's what we can prove. So let's use Kronecker substitution. Kronecker substitution to reduce the fpx case to z. I heard a funny story the other day from, I think from Kate, who's Canadian. I didn't know she was Canadian, but she said she's teaching American students, and they thought that Z was this guy, the integers, and all the other, you know, this little guy is Z. Yeah, they're all Z to me, except in the alphabet song, right? Because it doesn't rhyme. So how does the Kronecker substitution method work? So you're trying to multiply two polynomials in fpx. I'll just say this out loud. I won't write it down. What you do is you take your polynomials and you forget about p, right? You think of your polynomials as just polynomials with integer coefficients, right? And then what you want to do is you want to multiply these polynomials with integer coefficients and then reduce the result at the end modulo p. Okay, so how do you multiply in ZX? What you do is you evaluate your polynomials at a power of 2, and what that does, it just sort of plugs all the coefficients together with zeros in between them. It writes them down as a huge integer, and then you multiply those huge integers. And there's some homomorphism property of this evaluation map, which means that when you multiply the integers, you actually get the same result as multiplying the polynomials and writing their coefficients next to each other in a big long line. And then if you make your power of 2 big enough, then those coefficients won't overlap with each other and you can just read them off. Okay, so that's the basic idea. And what that proves is that you get mp of n is O of, maybe I'll call it b prime log b prime, where unfortunately b prime is a little bit bigger than this b. It has to be n times log of np. So you've got this extra factor of n in the log. It's coming from the fact that when you multiply the polynomials of the integers, you get coefficient growth. Okay, so an easy way to see this is suppose you're multiplying polynomials over f2. Okay, when you write down the polynomials over z, you'll just have coefficients 0 and 1. But when you multiply the polynomials, they're not just going to have coefficients 0, 1, they're going to get bigger. And they could get as big as log n bits, because you're adding n coefficients together. So you sort of have to leave enough room for that, and then you reduce mod 2 at the end. So you throw away most of what you compute. That's not a good way to multiply polynomials over small finite fields. Yeah? Yes, the question was, is this algorithm always more efficient than naive multiplication? The answer is definitely not. So the naive multiplication is going to be n squared, and that's the same for integer multiplication or polynomial multiplication, right? Now the problem is that this algorithm, this n log n algorithm, there's a really enormous big O constant here, right? I mean, in the paper, I mean, we were just trying to get this result theoretically, right? We didn't care about constants at all, so we were very, very fast and loose with our estimates. And I think we needed n to be bigger than, I think it's something like 2 to the power of 1729 to the power of 12, like some completely ludicrous number. Now, I'm sure you can do a lot better, and that's something I plan to work on in the next few years. I haven't got there yet. But still, the point remains that it's not suitable for small n, right? So there's always this tension in computational number theory between asymptotic results and real life results. What happens in practice is if you ask your computer to multiply two numbers, it will look like n squared for a little while, maybe up to a few hundred bits. And then you get into a region where they start using this Karatsuba algorithm. And then the exponent starts to decrease. It's not n squared anymore, it's like n to the 1 point something. And as n gets bigger, they throw more and more sophisticated algorithms at it. At the end, if you're using a GMP library, they're probably using a Schoenhager-Strassen algorithm, which is pretty close to n log n in theory anyway. And it will look almost linear. But it takes a while for that to happen, and the thresholds between the algorithms are determined empirically. It's almost impossible to work them out in principle. It depends on so many factors that are hard to sort of predict. Yeah. So I hope that answers your question. But as mathematicians, I don't care, right? If I'm just trying to understand these algorithms from the highest level, it's much easier just to say, I've got n log n, and just get on with my life, than to worry about what regime I'm in. I mean, you worry about that when you implement these things, but at this sort of theoretical level, I don't care. Any other questions? Okay. Right, so I was saying, so this is what you get, this b prime log b prime, and you get this extra factor of n. And you can check, if you fix p, like take p equals 2, and you try to multiply polynomials using this method, you will not get this. This ends up being something like n log n. You'll get n log squared n. So you actually lose a whole factor of log n. It's terrible. Anyway, it's okay for the purposes of this course, because we can now figure out the cost of this step 1, which I just erased. So the cost of step 1, which was computing h is f to the p minus 1 over 2, I can now work this out. So I need to know the degree. Well, the degree of h is O of g times p, because f has degree O of g, and then I've got this exponent p. So that's the degree of h. And so I can work out my b, which is my b prime, which is my bit size, my modified bit size, which is going to be O of gp times, that's n is gp, times log of n times p. So it's going to be gp squared. So that's my b, and I can simplify that a bit because that 2 comes out as a constant. So this is just O of gp log gp. So that's my b prime. Okay, and then I can work out the multiplication cost is going to be O of b prime times log b prime, so I get GP times log GP, and then times log of all that, GP log GP, and I can simplify that because all of this is just really no more than a power of GP, so this is O of GP log squared of GP. Okay, so this is the cost of step 1. Okay. And I don't think it really changes very much if you assume the thing we expect about polynomial multiplication. I don't think I've worked that out, but I think it ends up being more or less the same. Okay, the one point I want to make about this bound is that this is roughly linear in P. Okay, and this shouldn't be surprising because we have to write down a polynomial whose degree is roughly linear in P. Okay, we have to write down h at some point. So roughly linear in P, and this is a sort of starting point. We're going to be comparing all our future algorithms to this. Okay. Okay, let me talk quickly about step 2, which is computing this this inverse characteristic polynomial. So step 2. So this was computing this guy. Well, I don't really need to write mod P, right? Because this is already a matrix over FP. Okay, so for this, now I'm not a matrix multiplication guy. I'm an integer and polynomial multiplication guy, right? So this is now not my area of expertise, but I'll tell you the little that I do know. So let's write omega for the exponent of matrix multiplication. So what this means is we can multiply d by d matrices using O of d to the omega field operations in K. So if we have a matrix defined over K, we can use d to the omega field operations. I should warn you, in the literature there are some slightly different definitions of omega floating around. Sometimes people want this to hold for omega plus epsilon, for any epsilon bigger than 0, or something like that. I'll just stick with this simple definition. So the classical algorithm, if you just multiply out the matrices the way that you learnt in first year linear algebra, omega is 3. Okay, you have to do this, and then you have to do this, and so on. Strassen proved in, I think, 1969 from memory, that you can get omega is log 7 over log 2, which is about 2.81. It's a really short paper. It's like 2 pages. It's just a bunch of formulas. He says, do this, 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 and that's what you get. In terms of, I think, impact per page, it's really very hard to find another paper that compares. Yeah, question? So by field, I'm being a little bit relaxed about this. A field operation is an addition, subtraction, multiplication, division, one of those operations in K. I mean, you can do things more carefully, but let's just leave it at that for now. So this has been improved a bit since then. It's been a lot of work, as you can imagine, because once you know that 3 is not the right answer, it's really, really quite incredible. This to me is much more incredible than all the integer multiplication stuff. I think this is not well understood yet. The current record is omega is, I don't even have the whole number written down. I have 2.372 ... and there's frequently new results, and they're like fighting about the 8th decimal place or something now. It's really amazing. Some people think the answer should be 2 plus epsilon. So you can basically write down the product as fast as you can compute the product as fast as you can write it down. I have no insight into this. These algorithms are very complicated. Okay, let me just tell you a theorem, which I actually don't know the details of the proof. So theorem can compute the inverse characteristic polynomial of a matrix in O of d to the omega operations in K. So this is in the notes, this is proposition 2.5.2. So maybe I should say a word or two about this. So this is, I can't remember his name now. It's in the notes. This is quite a recent result. This is only the last 2, I think this is even post-COVID result. So you see, computing, I mean, this isn't really a hard problem. Computing a characteristic polynomial, there are pretty simple algorithms that will get you maybe d to the 4th, I think. You can get down to d cubed with a bit more work. The algorithms start getting complicated. What's really remarkable about this result, there's a few things quite amazing about it. First of all, it's deterministic, right? There have been probabilistic algorithms that do this. This is a deterministic algorithm. Secondly, it really does get you d to the omega. There's no extra epsilon, there's no log factors. Right? It is really on the nose. It is a constant time. It's a constant multiple of the time to multiply a matrix. Right? They reduce the problem to matrix multiplication and some polynomial arithmetic and some other stuff. So it's a bit of work. It's completely overkill for the result for the situation. I mean, the situation we're talking about, the genus might be 3. It's a 3 by 3 matrix, right? So for a 3 by 3 matrix, you don't care. You just go and calculate it, right? But for theoretical purposes, it's nice to know that you can do that. Okay, it's the same as the n log n. Like, you can't actually run the algorithm, but it's nice to know you can do it. Okay, so maybe that's all I should say about that. So let's figure out the cost of step 2. So each operation in FP takes time O of log P to the 1 plus epsilon. I should say what this means. So whenever I write a bound like this with an epsilon, I mean this holds for any epsilon greater than 0. And the big O constant might depend on epsilon. That's fine. So where am I getting this from? So let's just look at this for a second. So in FP, if you want to, so you represent elements of FP by just integers between 0 and P, right? So if you want to add 2 of them, that takes linear time. That's O of log P. If you want to multiply them, you'll get log P